All right, so now we have our class Bonahon. We'll continue this course on flags, snakes, and stingrays.
Okay, thank you. So today we had the flags the first day, snakes the second day, today stingrays. I'm supposed to do this, I think. And then, yeah. Okay, so I feel like I went a little fast last time, but last time we talked about, so first of all, we talked a lot about flag triples, which were characterized by triple ratio invariant. There shouldn't be an S here, but okay. And then we talked about quadruples. Okay, should I speak more softly? Should I whisper? So flag quadruples, which are classified by the triple ratio. So if a flag quadruple E, F, G, H, so you take the triple ratios of E, F, G, and E, F, H, and then we have this new invariant E, F, G, H, which was the double ratio. And I think I should have had this picture last time a little bit to explain the difference. I didn't spend much time explaining what this double ratio was. So the triple ratio, so what's this picture here? Well, for it's made up of two triangles, two discrete triangles. One is what we needed to define the triple ratios corresponding to E, F, G. The lower triangle is what we need to define the triple ratios of E, F, and H. And then you can put them together along this line going from E to F. And then the triple ratios were associated to small hexagons in the upper triangle or in the lower triangle for the invariants E, F, and H. And then the double ratio was associated to small squares like this. I should have had that picture here last time. I think it's a good way to understand what's behind the picture. And it's, so, you know, it involves four terms. It's a fraction, and the terms corresponds to these dots here, and you go below, above, below, above. That's top, bottom, top, bottom. That's what the formula said, and also it only involves the line here where one of the A, B, C, D is equal to 1. In this case, we're far from G, so where C is equal to 1, and same thing here. So this element here depends only on the full flag here, E, the full flag F, but only on the line of G and the line of H. Okay, but you know, if I draw a picture like this, you see, I put emphasis on, so it's a square, and I put emphasis on the diagonal from E to F, but because I looked at EF, I split it along this diagonal into these two triangles. But you know, my square, I could have split it the other way. Namely, instead of putting the emphasis on E and F I could have put the emphasis on G and H. I could do the same thing, and so then I would consider me and Mr. Larsen would consider the triple ratios of E, G, H and of F, G, H. And also the double ratio here. So these are the dots here. And what you see right away is that the hexagons here look very different from those hexagons. And the square here looks very different from that square because it's on a different diagonal. So these are completely different invariants. And for a flag quadruple, I don't see any reason to put one instead of the other. So we're going to learn how to go from this picture to that picture. And the amazing part is that it's actually nice. Okay, so if we switch from one diagonal here to that diagonal, that would replace these invariants here, putting the emphasis on EF to those invariants here where the emphasis is on GH. And that's what's happening. Okay, and so let's look at the next slide. So now we have to remember the horrible formulas that gave us these triple ratios and double ratios. But what you just have to remember is that they involve wedge products of elements in exterior powers in E, F, G, and now H. I should read the slide first before I start talking. So I was going to the proof. Yeah, so sorry, let me go to the theorem first. The theorem says that, so if I switch from the all the coordinates corresponding to one diagonal, let me go back. Yeah, sorry. Should nope. Okay, so here, associated to this diagonal, you have the old invariance, and associated to this diagonal here, you have the new invariance. And so what the theorem says is that if I want to determine, if I want to compute the new invariance in terms of the old invariance, this is given by a formula. Okay, that's not surprising. What's surprising is the fact that it's a rational fraction. Well, okay, that's probably not too surprising, but it's a rational fraction where all the coefficients, so the rational fraction is the quotient of two polynomials, and the coefficients of these polynomials are integers. That's probably not too surprising because we're doing combinatorics, but positive or non-negative integers. So the non-negative part is what's going to be really important here. As I said on the first day, I had never realized that being positive was so important, or non-negative. Okay, and so that's what the theorem says. And for the proof, and not only that, but the rational fractions are relatively explicit, although it's explicit in the sense of mathematics. Namely, yes, you can do it, yeah, in theory. You probably need a computer, however, to get the explicit formula. Okay, so now I go back to what I said, is that if I look at how these invariants are defined, they all involve wedge products like this, and you remember that these are elements in the exterior powers of E, F, G, and H. And well, these numbers, except that for the old invariants, we have C and one of C or one of D that is equal to 0. And for the new, because there is no, each of these wedge products is missing either G or H. And for the new invariants, they are missing either E or F, so that means that either A or B is equal to 0. Right? So, so it's a very restricted type of wedge products, but let's consider all of them. And to consider all of them, we pack them in the discrete tetrahedron, exactly like previously I had a discrete triangle, which is the set of ABCD, where ABCD are non-negative integers whose sum is equal to n. That's exactly that. And so here is a picture. So that's a subset of R4, but exactly like as before, if you project to R3, you get something like this. And it depends a lot on the projection. I'm going to go back to that. And so in the picture, so that's the same tetrahedron. I'm going to go back and forth. So here is the tetrahedron, and you can sort of see the same tetrahedron here. And the old invariants where we put focus on the diagonal EF, they correspond to those where C or D is equal to 0, namely that corresponds to these two faces of the tetrahedron. And the new invariants, the dots that are needed for the new invariants, they are in these two faces here where either C or D is equal to 0. And so that's a little bit the way we can understand the combinatorics. Okay, and so what's the next slide, I'm afraid? Okay, now there is a problem with this picture of the tetrahedron. And I tried. What do you see? I don't see anything. I don't understand very well what's happening here. In particular, before I drew the edges, then really there was no way that would look like a tetrahedron. And I tried to rotate, this is done with Mathematica, I tried to rotate a little bit and it's hard to see any order. So what we're going to do, we're going to rotate it in such a way and have a view where things are much more clear. And like this, you see a tetrahedron here, right? But actually, this picture is quite clear. So the way it's obtained, the tetrahedron, you linearly embedded in R3. You'd only need to know where the vertices go. And so you send the vertices to these points here. What that means, it's these 4 points here, except that this is in the XY plane. And there is the z-axis going towards your eye. That's why you don't see very much. And E and G. Yes. Did I do that? No, I think that was not the intention. I think I did something wrong here. I think I got the letters wrong here. So this point here is supposed to be up. This one is down. This one is up. This one is down. So that means, but the image is this discrete square here, the xy. So namely, it's a set of integer xy's where x plus y in absolute value is less than n. So namely, that's why you get this diamond. And then x plus, there is a, for stupid reason in the formula here, there is a congruence relation here. Okay, it's integers. When you do integers, if you solve things, you're going to have we may have congruence problems. And then Z ranks from the two faces below to the two faces above. And so you try to figure out what that is that gives you this. That's just calculus. I mean, pre-calculus, actually. And then there is another congruence requirement, which is that the class of Z is uniquely determined by X and Y modulo 4. Okay, that's so you do that by hand. So the main point is that each dot here is actually a stack of dots in on the same vertical line. Okay, and so now let's try to. This looks like a better, here I got my letters right. Previously they were not right. So this is the same picture, but now I'm going to look at the top face, namely the one I used for the old invariance. So the side view is this one, which is much more clear. This one, well, it's the same as before, but it's it's cut, it's bent along the diagonal EF here like this. So what you see that you have the two faces and they go towards your eye. So it's like this in front of you. Well, I call actually what I call a stingray is not going to, it's going to come later, but this is the top stingray, because the stingray, you know, it looks like a diamond, except it bends. Okay, so that's the top stingray. And similarly, for the new invariants, they are in the bottom stingray. So again, the top view is very boring because it doesn't look like anything, but it's bent this way. And I realized that I skipped the definition of a stingray here. So a stingray, what it is a section of the projection. Namely, previously, we had this view of a square. We have the square. And what we do is that we select a point in R3 above each of these dots here. So that's a section. And I want a certain Lipschitz type of condition, namely that if two dots are near each other, I want the z coordinate to not change very much. We're going to see, this is going to come up later. It's a very strong restriction. But it's we have to think of it as a Lipschitz condition because a stingray cannot bend very much. Come on, there are physical restrictions to that. Okay, so that's the top stingray, the bottom stingray, and then a typical stingray in between is going to look like this. You know, it's going to it's going to interpolate between the bottom stingray and the top stingray. So it's somewhere in between, like this. I will improve. I need to improve my pictures, but you know, I worked really hard to get them. So it's somewhere in between. Namely, at each of these dots here, you're taking something which is you select above each of these dots, you select a dot which is somewhere between the upper two faces and the lower two faces. Okay, now let's talk about the Lipschitz property. Remember, there was these, the Lipschitz constant was 2, if you remember, if you saw it. So there was Lipschitz constant of 2, and also there were some congruence properties. That doesn't leave too many possibilities. So what the Lipschitz property means is that if you have two dots here that are connected by an edge, so what that means is that they differ by plus or -1, and because of the congruence, if x differs by plus or -1, y also has to differ by plus or -1. No, it cannot be 0. I mean, because otherwise you would break the congruence requirement. And then I told you z is determined up to modulo 4 then. And so actually you switch from, the only possibility with that is that you switch from z to z plus or -2. And that's the only possibility. So, and exactly plus or -2. It has to change, cannot be 0. So what that means is that when you go from this dot to that one, the z coordinate goes from either +2 or -2. So in particular, if you want to describe this picture here, you can just put little arrows on the edges to figure out whether the z goes up or down. Because if it goes up, that has to be +2. If it goes down, that has to be -2. Which is this is telling you that there is nice combinatorics here, and actually, which also you can find in Fock-Goncharov in a different form. Okay, so that's the stingray. And now,
so the x is like you're looking at
x is like is the x of calculus.
So if I say x plus 1 is then 1, just 1.
This is 1. This is size 1 here, and size 1 like that. So my squares have sides square root of 2. Huh? Yeah, that's okay. I mean, it's you play with the picture. It's not it's not hard math, except for it would be pre-calculus, except for the congruence. Yes, yes. It depends, whatever, because the stingray is just a section. So there are many sections. And so actually, I'm going to change my section. And so there are moves, exactly like previously, there was the snake moves. So I'm going to have the equivalent of the diamond move, except it's going to be an octahedron move. And because the boundary is fixed, there is no boundary move. Okay, so there is only one move, which is the max to mean move. Namely, we're going to change a local maximum for the z coordinate to a lower minimum for that z coordinate. Okay, now let's try to think. If I have a local maximum for the z coordinate here, you remember that I can only go up or down by -2, by plus or -2. So if it's a local maximum, I have to, the z coordinate at all the nearby points has to be z -2. And then these are the xy coordinates. And so what I'm going to do is that I'm going to push down my stingray. And I saw that the stingray had a little bump. And so I go with my finger, I press on the bump, and then, oops, now the stingray has a little hole. That's what I do. And so if I do that, you remember that the class of z modulo 4 is uniquely determined. So if I push down, I have to push down by 4. And then you can check it's still a stingray because you move only by 2 here. But now I went from a local maximum to a local minimum. And it's not hard to see that you can go from any stingray to any stingray by doing that. I mean, it's a little bit of combinatorics. Okay. And the only problem is that these are the x, y, z coordinates in R3 because there I understand really the picture, but I wanted A, B, C, D. And so in the previous slide, I skipped that, but I don't know if you saw it. There is a formula to go from the ABCD coordinates to the XYZ coordinates. It's that one. It's based on the choice of these 4 points. Okay, again, pre-calculus. Okay, so you apply the formula and then, no, that's the other way around. I have a problem to tell the difference between past and future. So if you take this picture, but you express it in the ABCD coordinates, that's what you get. I mean, the same, okay. Just use the correspondence and don't try to understand what they mean. It's just there are formulas like this. But now in the ABCD coordinates, you want, so remember, we did this to consider all this wedge product of E, F, G, and D, and H. And that's what we were doing. There is just one little thing. So we wanted the wedge product. However, what you notice with the stingray, and so I was using the alphabetic order, but the alphabetic order, usually it's not mathematical. Mathematically, we like the counterclockwise order, perhaps clockwise if you want. And what you see on the stingray, so E and F are opposite. So E, F, G, H cannot be any kind of order on the boundary. And so we are topologists. We know that we should put that somewhere. And so the correct order is E, H, F, and G. So it's when I take the wedge products now, I'm going to be more grown up. Nope, that was the previous one. I'm going to go and I'm going to take E, the wedge product of EA, and then H, and then F and G, because that's the order around the stingray. So that changes what I had in mind by a sign, but signs are important because I told you that positive is going to be important. And so this guy, I'm going to abbreviate it as W for wedge product, ABCD. Okay? And so what you see, it's the old order, except with a sign in front. And now, if I think about it for my stingray, well, I went from this picture to that one. You see, the name of these dots here have not moved. The only dots that have moved is this one and that one. So I want to see how to go from the ABCD point to this one, which is given by this formula, A minus 1, B minus 1, C plus 1, D plus 1. But what that just means, it's X, Y, and then Z minus 2. Okay. And so that's, and it turns out that there is a magic formula here, which is the following. So I want to compare this guy to that guy, and if I take the product, I can express it in terms like this, in terms of the dots associated to the boundary of the square. So let's go back to the picture. So here you have a square, and I'm interested in the middle. And so it says it expresses the product of the wedges associated to the old wedge and the new wedge associated to the wedge products associated to the corners of the square. That's what the formula says. And where does this formula come from? There is a name that's called Plucker. So it's a famous formula due to Plucker, which have to do with the determinant in the old days, and now exterior powers. So the Plucker formula is famous because it's related to the Plucker embedding. And the Plucker embedding is an embedding of the Grassmannian in the projective space of the exterior algebra. So it's based on exterior products. And there are the Plucker relations. They determine they cut out. They determine the image of that embedding. Namely, this embedding is defined by the image is characterized by polynomial equations, which are exactly the Plucker relation. So there are many of them. But the first one is this one and has something to do with the Grassmannian of planes in R4. Okay, so let me be more precise. So if you look at this relation here, you see that all the terms, they have the A term is at least A minus 1. In the second slot, you have at least B minus B minus 1. And then third spot, you have at least C. So when you choose your exterior powers, it's smart to choose, you choose one for EA minus 1, but the next one, you can choose it, we have a freedom. So you can choose it as being the one associated to A minus 1 wedge with some element E. Like that. That's a smart way, and same for F. So the higher F, you take it with this smaller exterior power F, wedge a vector F, and so on, G and H. So you choose them like this. And the upshot of this is that these EA minus 1, EFB minus 1, GC and HD, you see them everywhere. So they are just like spectators. They watch what's happening, but they don't play any role. So in practice, what that means is that you work in the quotient space Rn, where you divide by EA minus 1, FB minus 1, GC, and HD. That's a plane. That's a plane, right? Yes. It has dimension 2. Oh, that's much easier. And then in the plane, you have a relation that if you take 4 vectors in the plane, so 4 vectors, which I'm going to call E bar, F bar, G bar, H bar to give you a hint about the proof. Then you take, I did something bad. Should do I click on which one? Did I do something bad? No. PC security. IT security. Oh yes, I was doing something bad. The police is going to come now.
Yeah, I mean, just our.
Okay, so it says that when I have 4 vectors, I take the determinant of the first 2 times the determinant of the last 2, but I put in the wrong direction because I have to go counterclockwise, remember? And I actually, yeah, no, that's, yeah, I should have written, it's not EFGH, it's EHFG. And so, and in this case, if I do it like this, and these are associated to the diagonals, and these are associated to the sides. Right? That's the way you remember this. I can use the side here a little bit. So the way you remember this formula is that you put E bar, H bar, G bar, F, and G bar. And so you see that the first 2 terms, EF, are associated to this diagonal and that diagonal. You take the product of the 2 diagonals, and sorry, and then this term here, that's EHFG, that's EHFG, and then the other term is EG times FH, namely, these are the product of opposite sides. If you know something about cluster algebras, that should ring a bell also. There is, so if you know the word cluster algebras, there are similar relations. So it's not too surprising. I mean, there is a close connection to that. Okay, so that's the Plucker formula. And the way you prove this Plucker formula, brute force with coordinates, come on, it's in the plane. So each determinant, if you take the coordinates, yeah, so each determinant, it's a polynomial of degree 2, so that and there are 2 terms. On the left, you have 4. Each product of determinants, you have 4 terms. When you take the sum of these 2, some of them cancel out, and the remaining 2 happen to be the ones, the remaining 4 are the ones you find here. Okay. I'm sure there are more conception proofs, but this one is good enough for me. Okay, and so there is this formula here, but what's really important is that you can rewrite it like this. Namely, you divide by this term. That's just what I'm doing. And what you see is that that expresses have you pushed down the stingray, the term, the wedge product associated to the new vertex on the stingray, this one here, you can express this into as a function of the elements in the old stingray. And in addition, you may notice that this is a rational fraction with positive coefficients. So you do it, and that proves the result. That proves that so as you go down, so first of all, So all the terms on the stingray, you'll be able to express them as rational fractions with non-negative coefficients in the wedge products associated to the top stingray, the old products here. And clearly, because the stingray, when the stingray moves from the top to the bottom, this is going to cross ABCD at some point. And so you're going to get all of them like this. Okay, but these wedge products. We wanted the cross ratios. However, not the cross ratios. We wanted the triple ratios and the double ratios. But the triple ratios and the double ratios, well, they are expressed in terms like this. I'm just rewriting the definition. It's just the formula where I used to have wedge products, and now I rewrite them in terms of this W. And there is a great thing happening with the double ratios. You might remember that there was a minus sign. And there was a minus sign because I was taking, quote, the wrong order in the terms. If I use this counterclockwise indexing way, then there is the minus sign disappears, which is really good. Okay, so all of these triple ratios, I was able to express it in terms of these wedge products. And then so the theorem says that every invariant in the lower stingray, namely any new invariants after the diagonal exchange, you can express it in terms of the old invariants by a rational function with non-negative coefficients. And so the reason for that is that when so the old, these new invariants, that's for instance this one, GHE, that's for instance this one here. So what you see, you can express it in terms of wedge invariants, and we just saw in the corollary, in the previous slide, we saw that you can express all these terms occurring in this definition here in terms of the wedge invariants that were in the upper stingray, namely the ones we were using to define the old invariants. Okay, so the upshot of this is that all these triple and double ratios, you can express them in terms of these wedge products here as a rational fraction with positive coefficients. Yeah, but we didn't want to use this one. We wanted to use the triple ratios and the quadruple ratios. Well, here it's a little bit combinatorial argument because we know that those guys, we know that the triple ratios, for instance, they don't depend on the choices of e to the power a, f to the power g, and so on, the choice of elements in the exterior powers. I know that if I multiply my choice of e to the power a by a number, then the ratio doesn't change. Well, that means that in my rational fraction, the e to the power a occurs as many times in the numerator as in the denominator. Okay? So that means, so that now I can use so in particular, because these are quotients of polynomials, these are I can rewrite the fractions in monomials that have in the W ABCD that have that property. And then there is a little combinatorial lemma, which is that if you have a product of products of W ABCDs that are independent of the choices, namely it satisfies this homogeneity property, then you can express them as a product and quotient of triple ratios and the double ratio. So there is a little bit of combinatorics after that, but there is no geometry. So we're done, and so that's how you end up expressing the new invariants as rational fractions in the old invariants. The great property of that is that if you knew that the old invariants were positive, then the new invariants are also positive. And also they are not zero, which is something we might have not known right away. So in particular, now I'm going to introduce, so I've been focusing on maximum span flag triples because flag triples and quadruples, because that was the optimum. For triples, that's really what I needed. For quadruples, that wasn't completely clear because the only thing I needed for the invariance to be defined was that the triple ratios were defined. And once the triple ratios are defined, the double ratio actually is always defined. I don't have to worry about that. So I'm going to say that a flag quadruple is positive if those triple ratios and these are well-defined and positive. So well-defined, that just means if you look at what, so first of all, I'm thinking of F1, F2, F3, S4 as the boundary of a square. That's the way to understand a little bit the combinatorics of that. And I'm focusing on this diagonal here. Yes, namely, I'm noticing I'm switching. We're going to consider flag P tuples. And so as a preparation, I'm switching the notation from EFGH to F1, F2, F3, F4. And I'm going to say that, so for them to be defined, I need the three flags in each triangle here to form a maximum span flag triple. And so, namely, satisfy the maximum span property. And here is a proposition. Well, it's actually a theorem because it's easy now, but it's a very fundamental property, which is that if I have, I didn't mean maximum span here, I erased maximum span, I was supposed to remove it. A flag quadruple is positive if and only if the one obtained by cyclic permutation is positive, and if and only if the one obtained by reversing the orientation is positive. Namely, being positive is invariant under the symmetries of the square. It's invariant under the dihedral permutation. A dihedral permutation, it's the composition of a cyclic permutation and a reflection. Okay, so the invariance under cyclic permutation, well, if you think about it, if you do cyclic permutation of those, you're just replacing this diagonal by that diagonal. And so what we saw is that, what we just saw is that being positive for one choice of diagonal is the same as being positive for the other choice of the diagonal. So that's how, so the invariance under cyclic permutation just follows from the hard work we did just in the past hour or so. And the invariance under reflection, on the other hand, is relatively stupid. It's due to what happens. So if you flip the square, what you're doing is that you're replacing this triangle here, but by this one, but with the orientation reversed. And what happens is that if you reverse the orientation of flag triple, well, if you look at the formula, you see right away that you're just reversing you're just taking the inverse. So in particular, if this one was positive, this one will be positive. And then for the double ratio, when you flip, you're exchanging F2 and F4, and which is like H and G. And again, if you for the double ratio, if you exchange S and G, you're just taking the inverse. So again, that respects positivity. So at this point, being positive is invariant, so it doesn't actually matter on how. It doesn't really matter how you choose the diagonal. Huh? And let me say, so I apologize, I forgot what I put on this slide. Yes, so it just say, yeah. So if you fix a diagonal decomposition, I think I already mentioned this. If you, I know I didn't for R3. So you want to know which invariance you can realize. So we saw in the case of R3 that it was really hard to know which invariance you could realize. You know, I had these funny these funny conditions which were not linear or anything. But here it's if you just take, but if you want your invariance to be positive number, there is no problem. Namely, you choose so for a flag quadruple, you have essentially two families of triple ratios and another family of double ratios, and they can be any positive numbers. And it's for the triple ratios, you need the hard work of the snakes. And then that part here, on the other hand, for the double ratios, it's much easier. Just a little simple argument using diagonal matrices. So then, okay, so we have so that gives us a one-to-one correspondence between positive flag quadruples and numbers. And but we were interested in the maximum span property, and the claim is that a positive flag quadruple satisfies this maximum span property. And the reason is because you remember we had W of A, B, C, D. I'm going too fast. Let me do it. Let me do it tomorrow. There is no point in rushing. Yeah.